Funding for this program was provided by the Annenberg CPB project.
Even after 3,500 years, the hieroglyphics on this ancient Egyptian obelisk stand out with impressive clarity. But this obelisk, known as Cleopatra's Needle, is in far less pristine condition. After lying half buried in mud for years, it was shipped from Egypt to the United States in the late 1800s. And placed in the very humid atmosphere of New York City. Here, the damp air reacted with natural salts absorbed from Egyptian mud to cause a great deal of damage to its surface. The reason for the contrast between the two monuments can be summed up in one word: weathering. Like the granitic rocks of the Egyptian monuments, all the rocks on the Earth's surface are affected by weathering, which is really the way rocks adapt themselves to the environment of Earth's surface.
Most rocks are formed deep beneath the Earth's surface or on the ocean floor. Tectonic activity, such as uplift, mountain building, or falling sea level, brings these rocks from their environment of formation up to the Earth's surface. There, the rocks are changed into a form that is stable under these new conditions by a process called weathering. Weathering occurs everywhere on Earth, be it a cold, dry polar region or the hot, humid tropics. This particular outcrop is made of granite. Now, granite in its fresh, unweathered state is quite hard because the individual mineral grains are tightly interlocking together. This granite, however, is heavily weathered. Quite soft, it crumbles easily because the grains are falling apart, and they're also decomposing chemically. Weathering occurs in two fundamentally different ways. The first of these involves the breaking of rock into fragments and individual mineral crystals.
The physical fragmentation of rock is known as mechanical weathering. The rocks we see are usually cracked to start with because of tectonic activity. Systems of natural cracks in rocks are called joints. One common kind of joint results from a process known as pressure release. The rock forming this great granitic dome in Yosemite National Park was originally buried kilometers beneath the surface. While a rock is below the surface, the layers of Earth's crust above press down on it. With tectonic uplift, surface erosion reduces the thickness of the overlying rock. The downward pressure is reduced, and the rock expands, primarily in an upward direction. At shallow depth, the expansion causes the rock to crack into sheets separated by joints parallel to the overlying surface. Exposed by erosion, plates of jointed granite then detach themselves and slide down, slowly unpeeling the face of the rock, layer by layer, like the stripping of skins from an onion. This is known as exfoliation, literally the stripping away of leaves. This opens the way for other types of mechanical weathering. For example, ice wedging. When water freezes, its volume expands as much as 9%. This expansion exerts enormous pressure, as those acquainted with burst water pipes in winter well know. We also see the effect of this pressure on roads in cold climates. After a particularly frigid winter, the water that has seeped under the pavement freezes and expands, heaving up the road surface. The same thing happens to rocks. When water gets into the cracks and freezes, it expands, wedging the rock apart, extending the crack, and even breaking the rock into pieces, which is what happened to form these jagged spires of granite. The term mechanical weathering, or disintegration, describes the natural breakup or fragmentation of rock at the Earth's surface. A chunk of granite, for example, may be broken up into smaller pieces by ice wedging or tectonic activity. But this doesn't change the composition of the rock. It's still granite. It still consists of its original crystals of quartz, feldspar, and ferromagnesian minerals. Contrast this with the other main form of weathering, chemical weathering, which has a much more drastic effect on rock, although the two types of weathering are interrelated. By breaking rocks into smaller pieces, mechanical weathering increases the amount of exposed surface. This hastens the chemical weathering of the entire rock. The principal agents of chemical weathering are water in the ground and moisture in the air. Usually these solutions are weakly acidic and are capable of causing the slow chemical decomposition of most rock-making minerals. As rain falls, for example, it dissolves small quantities of carbon dioxide in the atmosphere, producing weak carbonic acid. As this solution percolates through decaying vegetation and soil, it picks up more acids and thus becomes more effective in decomposing underlying rocks, especially limestone. This time-lapse sequence shows how rainfall gradually dissolves limestone. Thus, unlike mechanical weathering, chemical weathering actually destroys or changes the composition of the rock. The rusting of metal is a good example. The red rust on this nail is a different substance from the metallic iron at its core. One substance has changed into another. The iron of the nail has combined with oxygen from the atmosphere to form rust, iron oxides, the minerals limonite and goethite, or hematite. Because water is an important agent in chemical weathering, the degree of weathering is related to the amount of water existing in the natural environment.
The rate that a rock will weather is primarily controlled by the climate. If you have a very wet, moist climate, you have a lot more chemical weathering. The rocks will literally decompose at an accelerated rate. If it's a dry climate, only mechanical weathering will be able to operate, and that's a much more slower process to create soils.
In addition to water, temperature is important because warmer temperatures mean faster chemical reactions. As a result, weathering in the tropics is very rapid. Most deserts are also warm places, but here the absence of water slows chemical weathering. Eventually, most types of minerals chemically weather or decompose when they are at or near Earth's surface.
Only a few minerals are really stable at the Earth's surface. The mineral quartz, for example. Hematite, iron oxide, is stable. That's rust. It's stable at the Earth's surface. But most minerals are not. Most minerals form at temperatures very different than 25 degrees centigrade and 1 atmosphere of pressure. The minerals that are the most unstable at the Earth's surface and weather the fastest are those that form at the highest temperatures. Minerals that are the most stable and will weather the least are those that formed initially at the lowest temperatures.
Granite is composed of various minerals formed over a range of temperatures. Each mineral type responds to weathering differently.
Here's an example of a granite that's fresh, it's unweathered, and as I try as I might, I can't break this rock apart. We can see the dark gray quartz and the pink orthoclase feldspar. They're in the rock, but they haven't weathered. We'll now turn to another granite that has already begun chemical weathering. It's starting to fall apart. And we find that the different minerals are proceeding differently. Plagioclase is weathering the fastest and has already turned to clay. Orthoclase feldspar is starting to weather as well, but the quartz has not weathered at all. But the basic framework of the rock is beginning to fall apart. And now this rock, while I can begin to break this rock apart with my hands, it is starting to decompose. And this is how a rock changes to become sediment. The grains are breaking apart and are dislodged and now will fall into the sedimentary system.
These grains accumulate in piles called grus. As sediment is washed away by rivers and streams, sand-sized mineral grains may be sorted out, deposited, and cemented to eventually form sandstone. And the silt may accumulate separately and harden as siltstone.
Weathering is essentially a process of destruction, involving the physical and chemical breakdown of the parent rock. But it's a natural process, one that's been active throughout geologic time. With the advent of the industrial age, man has upset this natural balance by accelerating the weathering process. The billions of tons of carbon dioxide, nitrogen oxides, and sulfur dioxide that we add to the air each year from the burning of fossil fuels and forests creates far more problems for the atmosphere than sometimes turning it brown and making it unpleasant to breathe. These gases combine chemically with the rainwater, in some cases creating solutions that are hundreds of times more acidic than natural rain alone. The effect of this caustic precipitation falling on the Earth's surface creates a serious global-scale environmental problem, commonly known as acid rain.
The most important source of acid rain is the sulfur dioxide emitted by automobiles and factories burning high-sulfur coal. This combines with moisture in the atmosphere to form sulfuric acid. Additional acids can form from carbon dioxide, carbon monoxide, and nitrogen oxides from auto exhausts and from burning of almost all kinds. The excess acids in rainfall accelerate chemical weathering of masonry and stone downwind and can wreak havoc on the leaves of plants and trees. A striking effect of acid rain is the historical deterioration of some forests and lakes. Over the last 40 or 50 years, the woodlands of Central Europe and Eastern North America have been noticeably affected by acid precipitation and related dry pollutants. And with continued industrial pollution, the process compounds year by year.
Although weathering is fundamentally a process of destruction, it has the beneficial effect of breaking rocks down into soil, which is essential to all land-based life. Humans could probably live without oil or coal or wood to burn, but we wouldn't survive without soil. Soil has many functions. It's the habitat for land plants. It harbors bacteria, which produce nutrients essential to these plants. And it's the storehouse for water and for trace elements, which, by the way, are also produced by chemical weathering. In fact, soil is the foundation upon which the entire terrestrial food chain depends.
Consider, for example, calcium and phosphorus, two of the essential elements in bone. Calcium is abundant throughout nature, but animals obtain phosphorus primarily by eating plants, which absorb the phosphorus from the soil in which they grow. The most important original source of the phosphate in soils is the relatively rare mineral apatite. The apatite in a chunk of granite the size of a fist would probably fit onto the head of a pin. But when granite is weathered into soil, the tiny apatite grains decompose, releasing soluble phosphate, which is subsequently taken up by plants. and then through the food chain by people. Apatite is found in many varieties of rocks, though usually only in minute traces. Still, it is the major source of all the phosphates so vital to life. If it were not released by weathering, no vertebrate land animals could exist. Soils are formed as a result of the mechanical and chemical breakdown of rock. They are enriched by the decomposition of plant life, which produces the rich organic matter known as humus. It's this combination of weathered fragments of rock and humus that creates the most fertile soils. In essence, soil is a thin layer that rests on bedrock, like a coating of rust on iron. As the soil matures, it forms into several different layers, or horizons. The A horizon is the loamy topsoil gardeners know so well. This is where most plant humus is derived. Rainwater seeps down through this layer and washes or leaches some of the soil materials down to the B horizon, the next layer where the leached materials accumulate. The C horizon, the bottommost layer, is the zone where the underlying bedrock is partially disintegrated and decomposed, but still recognizable. The nature of a soil is determined partly by what sort of parent rock it develops from, because this is its prime material. If the parent rock is granite, it decomposes into a sandy soil made up of quartz grains. Clay in the soil comes from the weathering of feldspars. Such soil is usually permeable and can easily nourish vegetation. A fine-grained rock, such as basalt, decomposes more rapidly to clay minerals and iron compounds. Basalt forms soil that is generally darker and less permeable than granitic soil, but still fertile. Climate and time also play important roles in the evolution of soil. As time passes and the soil matures, it progressively loses the signature of the rock it was formed from and takes on characteristics determined by the climate. Fertile soil doesn't come into existence quickly. It took about 15,000 years for this layer of transported soil, less than a meter thick, to develop in the American Midwest. Soils in the tropics can develop faster, in a few thousand years. These millennia of soil evolution can be destroyed in a few short years when certain types of human activity disturb the surface. For example, soil can be destroyed by poor soil management, such as overgrazing or overworking the land, or simply cutting down too many trees. One region that has been adversely affected by this is the tropics, where the jungle floor would seem to be the most fertile environment possible. Clearing the land for agriculture has, in many places, been a disastrous waste, because the floor of the rainforest is actually a rather unproductive soil. Where, then, does all the luxuriant vegetation come from? The fact is, the tropical rainforest creates its own nutrients in the form of humus, a thick layer of decaying trees and plants. But because of the intense rainfall in the tropical jungles, nutrients in the soil are quickly leached and drained away. So, when a forest is cut down, the humus is exposed to erosion. The loss of this nutrient source ultimately results in a barren wasteland. Soil erosion is not limited to tropical rainforests. It is, in fact, a worldwide problem that can take many different forms. In the 1930s, the American Midwest experienced a catastrophe of major proportions, the Dust Bowl. Drought conditions combined with high winds to blow the region's soil into massive swirling clouds of dust.
The famous Dust Bowl of the American Midwest occurred between 1934 and 1938, and the natural circumstances that led to that catastrophe really were not unusual. High seasonal winds are common in the Midwest, and drought occurs cyclically. It's a common part of that environment. What was unusual is the fact that the grassland there had been removed by agriculture, by grazing, and the loose soil underneath, a lot of which is dust blown in from past glacial events, was free and exposed to the wind, so away it blew. And this was a catastrophe that didn't slow down. It continued because of a sustained drought.
Plowed fields were stripped bare of topsoil. Planted crops were ruined, buried in piles of dust. For many farmers, the result was bankruptcy.
Well, in retrospect, a lot could have been done to prevent the disaster of the Dust Bowl, but of course in those days we didn't know as much as we do now about these problems, and so it's not a surprise that it happened, and no one can really be blamed.
As a result of the Dust Bowl, the United States Soil Conservation Service was established in 1935. Its goal was to develop farming techniques that would help to protect this precious natural resource and to prevent similar disasters from ever occurring again. For farmers in the Mojave Desert, the issue of soil management is a matter of ongoing concern. There are multiple factors that threaten soil and crops in this region, ranging from erosion to limited water resources. Because of the complexity of these soil management issues, farmer Wayne Soapland turned to the Soil Conservation Service. Rick Aguayo, who works for the service, then made the first of several trips to Soapland's farm. His immediate goal: to analyze the overall situation and come up with a soil conservation plan.
We discussed what was needed in this area and what conservation practices I already had in place, and he made certain suggestions on how things could be improved, and we went on to creating a plan out of those suggestions.
Once we get into to make the decision, yeah, I want to have a conservation plan, we need to determine what his objectives are. What's he planning on doing with that property now, 5, 10 years down the road? Once we do that, we start evaluating what the resources are, what the soil resources that he has to work with, what are his farming operations, his irrigation system.
At the heart of the conservation plan is an in-depth soil survey to determine the precise kind of soil on Soapland's farm. Once Aguayo analyzes this, he can recommend a very detailed set of conservation practices. Many of Aguayo's specific recommendations are designed to overcome erosion, one of the most troublesome threats to Soapland soil.
Our major problem with soil erosion results from the wind, and that can happen at any time of the year, winter, summer, fall, doesn't matter, and we have fairly heavy winds for long periods of time, and we have to take a number of precautions related to that.
One of these precautions, a barrier known as a windbreak, is composed of very tall trees. Wayne Soapland has relied on this technique to protect his precious soil from the ravages of erosion for a long time. The windbreaks also protect Soapland's farm from being smothered by drifting sand. As Soapland has learned through the years, a windbreak is extremely effective, provided it's sufficiently dense and tall. When there is an opening in the protection, or no windbreak at all, the damage can be severe. But windbreaks are not the total answer to erosion problems. A technique called conservation tillage has also proved to be especially useful. Tilling, or plowing the fields, is routinely done to prevent the formation of residues which block the percolation of water through the soil. But if too much tilling is done, the soil is so frequently loosened that much of it can be blown or washed away.
In other words, instead of plowing the soil and disking it a number of times, leaving it completely exposed, we do as little as possible. We will disc once, leaving as much stubble on the ground so that if a windstorm comes up during that time, the very little dirt is moving. And then we get back in and try to plant the next crop as soon as possible and begin the irrigation, so that the period of time that the soil is exposed is very minimal.
Another concern for both Soapland and Aguayo is irrigation management. They recognize that the right amount of water is critical, not only for the immediate needs of the crop, but for the long-term health of the soil as well. Too little water would parch the fields, while too much would result in the formation of saline residues and cause root problems.
In this case, Wayne has sprinkler irrigation systems that a lot of the farmers are using either wheel lines or center pivots, and basically try and design them so that they provide the optimum moisture for the crop while reducing erosion and groundwater contamination, etc. We don't want to overwater.
In addition to his suggestions concerning tillage and water management, Aguayo has set up a crop rotation sequence designed to maximize the productivity of the soil. Along with the use of windbreaks, these soil conservation techniques have already made a significant difference on Wayne Soapland's farm. What's especially gratifying for Soapland is that these improvements are not just quick fixes, but significant changes that will keep his soil productive for years to come.
Thinking of soil as just another pile of dirt is an extremely short-sighted notion. Without soil, without dirt, life on land could never have developed and flourished as it has. It is our responsibility to protect and preserve this valuable resource. But beyond that, it's important that we respect and understand the entire weathering process. Otherwise, we run the risk of upsetting a delicate natural balance of physical and chemical factors that have combined to support terrestrial life for over 400 million years.
Funding for this program was provided by the Annenberg CPB project.
For more information on the college telecourse, video cassettes, off-air videotaping, and books based on the series, call 1-800-LEARNER.